This unit, Exponent and Radicals, explores a very, very useful part of math where we say instead of just having a number on the same line, like I say a multiplication, which would just be a kind of a normal operation, we have a way of condensing a lot of other operations through a power specifically. Now, to type this in on some calculators, you might have to type in a special character with a caret beside it to get it to raise it to this power. And this exponent, this power that we call, there's different names that we give this. Most of the time we call it the power. It's in the exponent position. It's condensed. It's showing a lot of things that just we don't want to really write out. What I don't want to be writing out is what 2 to the 4th is summarizing, that we're multiplying the base of this power. We're multiplying the base by itself 4 times, which is a whole lot of writing, which is why we summarize it and condense it. And sure, we can eventually get this to a single answer. And, we could say that this is when we expand it out. This is the standard every single day, everyone in the world, normal number. When we talk about numbers, it's usually just the standard normal numbers, but then we can also keep it in exponential form, the exponent form. And this becomes quite handy, especially as numbers get really, really big. You might notice in science, scientific notation, for example, uses numbers like 10 to the 8th. Because I definitely don't want to be writing out 10 times 10 times 10 times 10 times 10. Expanded form would just be kind of silly at this point. And even the standard position number, 1, 2, 3, 4, 5, 6, 7, 8, that's getting quite difficult to write out and even read. You got to sit there and be 100 million. 10 to the 8th. So much quicker, so much more to the point. Even with negative exponents, which is a part of this unit, if you get into physics, if you get into the mass of an electron, they have to get really, really, really small. And maybe they have a number like 10 to the negative 13, which is a very, very small number. And I absolutely don't want to expand that out. That's a whole lot of tens. But what this negative means, partially just as initially, is that I'm actually moving the decimal place to make the number smaller. It's like a division of 10. And if I was to write this out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, boom. That's what that number is representing, but all packed in these exponents. Incredibly powerful. See what it did there? But incredibly powerful, very versatile. And instead of writing these ridiculous numbers or these ridiculous expansions, we really, really want to use these exponents. So what happens when we start wanting you to multiply, divide, add, when we start wanting to work with these in other mathematical ways? So let me look at some laws. The first thing that we have to kind of teach you in Math 10 is how to work with these in a variety of scenarios. Now, if we asked you to say take something like 2 to the 4th and multiply that by 2 to the cube, 2 cubed. There's various ways about this. Ideally, we want to keep the power part of the calculation. Now, part of the learning of this is that what does this look like if we were to expand this? 2 to the 4th multiplied by 2 cubed. And this is trying to lead us to the answer here. Because if you look at this totality, all the things that we're multiplying, there's 7 2's. There's 7 of them. And even though the operation might appear to say multiplication, the powers are working off of a different law because we're not actually creating 12 twos, as you can see below here. There's only 7 of them. And the correct reaction to a statement like this is not to even multiply the bases. Those bases are staying exactly the same. In fact, they have to match throughout the whole question. There's not a single base in this question that's going to move or change, but we're going to be adding these exponents as shown below, that there's just a total of 7 of those base 2's. And when we keep it in exponential form, we could say use this law. It's called the law of addition, where multiplication in the land of exponents, multiplying means add, especially if you're staying in exponent form. This will work. This is the same logic that I can use if I take something like 8 to the 10th and ask you to divide it by 8 to the 4th. Now, if I was to expand this, 8 times 8, oh, why did I pick such a big power here? Come on. There's 10 eighths, and here's 4 eighths. And this is what it's kind of ridiculous to sit there and expand out these questions, but it does maybe help us understand where the power comes from. The nice thing about this is that they're not going to combine and create a total of 7 like in the last one. They're going to reduce with one another because each 8 can cancel with another 8 that's on the bottom. But they don't all cancel, but it leaves only a few left. There's only 6 eighths left. And how do you find out what's left? Is that we are asking you to understand that we're not just going 10 divided by 4, we're actually going 10 minus 4 to get to the simplest expression, keeping it in exponential form. Remember, the base matches the base, matches the base, matches the base. The base stays consistent. We're using exponent laws to do this work. Lastly, another really critical law here. Let's say I have 5 cubed. How do we react to this? Now, what this means is if I expand, here's 5 cubed, and cubing that means that you have to multiply that by itself 3 times and total them up. You can see it. How many 5s are there? How are these numbers going to be combined correctly? Because I see 9 5s when 3 is taken to that third power. This is called power of a power. Hopefully this shows you exactly what's going on behind the scenes. The base stays the same, 3 times 3, and leaving it in exponential form, we would get 5 to the 9th. One issue that happens in some of these questions, like if I have 6 to the 4th power, but I'm dividing it by a larger power, like 6 to the power of 6. This creates a really, really tricky situation. Hopefully it kind of makes it a little bit clear what we want you to do when we expand this. Now, using this law we've already done, subtraction law, you might be able to say, well, this is simple. 6 to the negative 2. But we don't like negative powers. We really don't. We try to avoid them. They are kind of a sneaky thing we try to get rid of. Now, in exponentially expanded form, this is a way of showing what a negative power is, literally is. Now, dividing, in theory, means that all of these common bases can be canceled, because division, 6 divided by 6 is 1, and a whole bunch of them cancel. But not all of them cancel. How many survived? Well, there's only 2 left. But they're not left, I can't just say there's 2 left, 6 squared, because they're not in a normal position. They're actually on the bottom of a fraction. And we have to keep the ratio. Remember, when you write fractions in math, they're supposed to be representing some sort of ratio, the top balanced with the bottom. And that's what this negative power means. This negative power means that there's 2 6s left on the bottom, the denominator of a fraction. Oh, that's a terrible M. No, I'll fix that. It's bugging me. No, I ruined my O there. On the bottom, as you can see in exponential form. So in the effort of trying to keep positive exponents, even though they're left on the bottom, is to maintain the fraction and leave it as 1 divided by 6 squared. Which can be that this is a big one here. This is something we're going to pick on in Math 10C. Now, here are the laws, and most of the unit falls from these laws when we want you to work on these powers. So here I go. Here are some typical examples in topic 1. They want you to take something like 2x squared to the 4th, multiply that by 3x to the 4th. There are some exponent parts. And there are standard numbers mixed in together. Standard numbers don't have fancy laws. 2 times 3 is 2 times 3, if that's what we're going to work on. But in the land of bedmass, we are now really needing you to do that exponential step first. And there is this power, which is working on everything. It's a grouping of it. It's outside of a set of brackets, which means that power of 4 is for that entire group. We have to do that first before we could think about combining things in any other part of this question. And so there are 2 steps. To get to the next step, not only do you have to know what 2 to the 4th creates, but you have to know what x squared to the 4th creates, because not only is the normal standard number collecting that power, but so is this base x squared also being taken to the 4th power. So there's 2 kind of different things going on here, but 2 to the 4th, 2 times 2 times 2 times 2, would build 16, and x squared to the 4th, multiplying those powers together, builds an x to the 8th. The first stage of bedmass is complete. The only thing I see left is multiply. We need to multiply these numbers together. However, it is important to note again that we have a standard number multiplied by a standard number. They belong together. They will talk. They don't want to talk with the x's, because those are what called our different bases. That has to be the same type. X's will talk to x's. They are the same kind of term mathematically, and they can combine using the exponent laws. But we focus in on these numbers. What is 16 times 3? 16, 32, 40, 50, 48. And I got to add these powers. That's the exponent step that we really want to work on here. This is where we go 8 plus 4. The base stays the same, but now it's x to the 12th. And we mix questions like that in different various ways. And you got to be on the lookout, because not every number multiplies by every number. And there are exponent laws hiding in here for those bases. A quick shout out to a very, very special power in topic 2. We briefly kind of want to talk about what it means to have a fractional power. And just to point out some of the intro ideas here, this is the root. When we put a power on the bottom of a fraction like this, it's asking you for a root. And the squared root, which is the most common root, this index 2 squared root, that's kind of our most popular root. And so we sometimes would now just say, well, why write that power like that? It looks funny. Let's just write it as a root over x. And we can extend this, because now if I put a 1/3 power, actually let's make a nice base on this one. Let me just go 8 to the 1/3 power. That's a nice little symbol. And it's trying to tell you that this is a root, but not a normal squared root, but a cubed root. So we would be able to change over this symbol into the square root of 8. Cube root of 8. Which leads perfectly into the third topic of our exponents unit, which is to teach you how to take roots. Now, for the most part in this topic, we give you perfect roots. Where the idea comes from. If I drew a square, and this square had an area of 100 square centimeters, how big is the side? Which is like, essentially, through some logic, asking you to take the square root. Get it? Square root of 100. This happens to be an incredibly perfect number. Sometimes when you take square roots, you get weird numbers, you get decimals, but not this time, because square root of 100 is exactly 10. Why? Because 10 times 10 would have built the 100. These sides had to be 10 each, because 10 times 10 built the 100, and they're both equal to each other because it's a square, because all these, in a side, all the squares equal to each other, and that we call the root. After we take the square root, that becomes the root of 100, the square root of 100. Now, this is not the only kind of root we would ask you to take. If I extended this and drew a cube, a perfect cube, all the lengths are equal. And I told you that the volume of this cube was 64 meters cubed. How big's the side? We could work backwards through this cube. And through our logic and through our knowledge of formula, perhaps, or how we could work backwards here, I wouldn't take the square root, since it would be asking for something times something times something, 3 multiplications to build that 64. We call it the cubed root. It's not a pun. It is literally talking about cubes that we're solving. Cubed root. And if I took the cubed root of 64, you would be quite happy about this root. This is a perfect root. It doesn't come out to a decimal. It doesn't, come out to 18 or anything like that, 18.2, anything like that. It comes out to exactly 4. Why does it come out to 4? Because 4 times 4 times 4 would have built 64. That's why. And that is called the cubed root of 64. Every calculator you can find a square root and a cubed root on it to take these perfect roots. In topic 4, we start asking you to take roots that aren't so perfect. There's not that many perfect roots out there. Let me show you a few of them. Square root of 4, square root of 9, square root of 16, square root of 25, the square root of 36. There's the first 5. There's more, but you have to skip quite a few numbers to find a perfect root. These are all perfect. Use your calculator and type them in. I promise you, you won't get a single decimal. You're going to get a nice number. Soon, even nicer. One of my favorites. Great. Perfect. These are all perfect roots. As in, when you work them out, they are exact. There's no decimals. It's not awkward. It's not irrational. Perfect roots. Now, completely opposing that are the roots like square root of 5, square root of 10, square root of 11. Now these are the worst roots to work with because they just give you like an endless decimal. There's just nothing you can do with the square root of 5. Maybe you can write 2.236067977, but that's only what my calculator is going to show me. It doesn't show me all the decimals. This thing keeps on going forever. It's a really, really awkward number. In fact, this is called irrational. It's an endless, non-repeating number, and if you're delta root like this, you're kind of just stuck with it. It's not really going to do anything, and because this is irrational and so awkward to write out, we actually would just why not just leave it like this? Just leave it like root 5. Who cares about that decimal? It's a terrible decimal. It's not exact. Let's leave it in this form. This form is actually an advantage because it comes out with decimals. So we have to play with both of these now. We now give you mixed radicals. Mixed radicals will always have one perfect part and one irrational part. They're mixed, perfect and irrational. You just got to find them. Here's an example of a root that is mixed. The square root of 20. Now, if you type in the square root of 20, it just looks like another one of these lame roots that it's just a decimal. But don't be fooled. Don't be fooled. One of these nice roots are in it. And we call this factoring. What are the factors? How do you build 20? Here are all the factors. Here are all the ways that you can build a 20. This is multiply. 1 times 20, 2 times 10, 4 times 5. Now, are any of those factors in the perfect list? The perfect root list? And the only one I see is 4. This is the best way to factor 20. So what we're going to be doing is saying, well, 20 is a blend. It's mixing the perfect radical and a terrible irrational radical. That's where 20 is coming from. 20 is not all bad. It's only half bad. This one is perfect. This one is very unperfect, flawed, but we're not going to be able to fix it today. But we can work on this one because it's perfect. Remember, taking the square root of 4 comes out to 2. beautiful, perfect square root. So we're allowed to take the roots of perfect ones. We're not allowed to take the root of irrational, and we create a mixed statement, which is what topic 4 wants you to know about. And that leads me exactly into the last topic of exponents and radicals. And it wants you to know a lot about the number systems. It wants you to know about the real numbers. And there's, a number like picking a random number, but the number 11. There's a lot of things I could say about this. It's a natural number. It's a whole number. It's an integer. It's rational. It's real. And this topic kind of just wants you to know what I mean. These are different groups of numbers. And a number can be in lots of groups. It fits all of these definitions. Blue, blue. All of those definitions. And if you look up those definitions, and if you kind of do a little bit of the reading out of the workbook, you can see 11 is a wonderful number. Now, what we kind of want you to, the main one that we want you to be able to distinguish between is rational versus irrational. Rational numbers are exact. Irrational numbers are not exact. They are endless. They don't repeat. And you can't really ever know exactly what they are. We come up with symbols for them. Most famous irrational number is pi. There's no no one knows exactly what pi is, because it just keeps on going. It just, you would need, the bigger the computer. People have built supercomputers that have stored billions and trillions of decimal places. I mean, my calculator only gives me the first handful. My calculator is by no means a supercomputer, but since it just keeps going and going and going and going, and it never ends. In theory, I don't know what the next number is. So I don't know exactly what pi is, because I can't predict the next numbers. And I would need a bigger computer. We would need every computer in the world, and we would still not have enough computing power to figure out more decimals. Eventually, we just run out of space, because they are infinite. Infinitely complex. Totally irrational. Now, a number like 1 divided by 9, type it in. It's 0.111111111111 and does keep going forever. But could you predict the next number? Could you predict the number 100 spaces, decimal places from now? And of course you could, because there's a pattern. It's super predictable, and I know exactly what 1 over 9 is. It's exactly 0.1 repeating. And that's exact, rational. Rational, if for me, makes me think of fractions. Any fraction is rational if you can build it out of a fraction, like 1 divided by 3, 1 divided by 4, -6 divided by 7. These are fractions. They are going to have a pattern. They're going to create a decimal that you could predict. But things like symbols, really awkward radicals, those are going to be incredibly impossible to predict, because the decimals don't have a pattern. And for the number systems, that would be kind of the highlight that you could start with. Thank you.